Good afternoon. It is my privilege to introduce Matt Minniear, who will be presenting the work he did for PCI Skanska. Thank you.
Thank you, Derek. Thank you, Dr. Marco. The goal of this project was to design an upgraded distributed control system for the CPS OW Summers generating station, specifically their burner management system, and more specifically for Unit 2. A brief overview of the parties involved. PCI Skanska, a local, Evansville-based engineering firm, has been leveraged to complete the control system modernization. PCI Skanska specializes in EPC, or engineer, procure, construct projects. They are able to offer clients a true turnkey experience through engineering, material procurement, and construction services if necessary through their partner IC Skanska. PCI Skanska serves as the Midwest headquarters for Skanska USA. As of today, Skanska USA is the 6th largest contractor in the United States. The Power Generation Controls Group, whom I worked with on this project, specializes in control system modernization projects at existing generating stations. The utility company involved is CPS Energy of San Antonio, Texas. They were acquired by the city of San Antonio in 1942 and they are the largest municipally owned utility in the United States. They serve just under 750,000 electric customers and over 330,000 natural gas customers. An interesting fact about CPS Energy, they do not pay taxes. In lieu of paying taxes, they provide revenues directly to the city of San Antonio, and as of today, that comprises 25% of the city's annual operating budget. CPS generates power through a very diverse mix of fuels. The 2 units at the Summers station, this project, are natural gas. They comprise and are part of the 42%. Other forms of energy are nuclear and coal at 14 and 28%, and 16% renewable. That renewable energy is made up of wind farms, the majority, solar arrays, and landfill-generated methane gas. An overview of the project and project requirements. As mentioned previously, the control system for Unit 2 Burner Management System, or BMS, is to be upgraded at the Summers Generating Station. This project consists of 525 BMS points. Those points can be thought of digital inputs or digital outputs. There are analog points associated with projects, none for this particular project, however. The upgrade will consist of converting an outdated logic manager to a more modern distributed control system, Honeywell's high-performance process manager system. There are 3 main project stipulations. Number 1, that the existing logic manager cabinets be reused first before adding any new cabinetry. Second, that all field wiring terminations heading into the cabinets remain in place and undisturbed. And 3, all existing wired spares out to field-connected devices or marshalling locations remain intact. An overview of a distributed control system. So rather than a centralized brain providing the control, the elements are not in a centralized location. Each subsystem in the plant uses a separate controller. An example of other subsystems within plants are data acquisition, motor control, soot blowing, ash handling, and boiler water circulation pumps. The controller receives information from its inputs and directs or sends information to its outputs. In this slide, we can see an example of a digital input card. The easiest way to think of a digital input is a light. In this example, we have a field-connected device. Could be anything from a contact to a limit switch. When a condition is met, the contact in the field closes, thus completing the circuit. This allows an indicating light to light at the control cabinet. It may be indicating that a valve is open or closed, or that a process is commencing. When the contact opens, the circuit is broken and the light turns off. Conversely, a digital output can be thought of as a switch. Again, when conditions are met at the DCS cabinet, a contact closes, completing the circuit. This allows a particular process to commence in the field. In this example, a valve will be opened or closed. When the contact opens, the process of the valve ceases. Honeywell's High Performance Process Manager, or HPM, was selected for the control system migration. The main reason for this selection is the balance of plant is on this control system. It is made up of 3 distinct controller pieces, the first being the High Performance Process Manager Module, or HPMM. This device performs all signal processing and operation and serves as the connection point to the Universal Control Network. Next is the Input-Output Processor Module, or IOP. This piece of hardware is responsible for all signal conditioning and data acquisition. Finally, the Field Termination Assembly, or FTA, provides the connection point for the wiring from the actual field devices. This diagram shows the network interconnections and its hardware. The 3 items in the red rectangle represent the scope of this project. On the bottom row, the marshalling or field device is connected to the Field Termination Assembly, which in turn is connected to its Input-Output Processor and High Process Manager. This is connected to the Network Interface Module. This NIM can be responsible for several subsystems within a plant. Finally, the NIM is connected to the Local Control Network. This is where the operator interface or console is in the plant. The project database is received in a Microsoft Access file format. Each row within the database represents a system point. Thus, this project's database has 525 rows. The columns represent the attributes of those individual points. A typical project database will have more than 50 columns of information for each point. The point index, in this case, the first column, is a unique identifier. It will not change throughout the duration of the project. It is used to track the point between the database exchanging hands between third parties. It can uniquely identify each point no matter what part of the process of the design it's commencing. While the other attributes may change, that unique point index remains constant. After receipt of the database, partitioning takes place. Partitioning creates system redundancy in different locations of failure within the DCS cabinets. Those locations of failure include the card or module itself, the power system, the backplane that the cards plug into. There are many locations of failure. The first step when partitioning a database is to assign a signal type or voltage to each point. 3 voltages were considered for this project as they are the only 3 present in the burner management system. There are 120 volts AC, 125 volts DC, and 24 volts DC. The next step is to group those points by input-output type. Again, as previously mentioned, only 2 types are present in this project, digital inputs and digital outputs. The next step is to use the schematic diagrams provided by the plant to determine where those points are currently housed, i.e. where they're addressed on the current cards. And then finally, non-redundant points are assigned to new cards. This completes the design process. Here we have a display and an example of partitioning. In the example on the left, we see a non-redundant scenario. In this case, we have a new digital input card with 32 points. Pumps A1 and A2 and B1 and B2 are not redundant. Therefore, they may be placed on the same card. If this card were to fail, all 4 pumps would be taken out of service. In a redundant scenario, the A prefix pumps were determined to be redundant of the B prefix pumps. Therefore, they must be placed on separate cards. Also in this example, additional valves were placed on the cards. This is not necessarily the case. These points or addresses may be left as spares. After partitioning, an accurate hardware count can be compiled. The following lists the individual pieces in the counts. For this project, 1 redundant HPMM set is required. And a set of HPMMs can power 41 different IOPs or FTAs. 31 input-output processors were required as a part of partitioning. 13 of those being digital outputs, 13 of those being digital inputs rather, and 18 being digital outputs. 31 total field termination assemblies were also required as a part of this project. 2 of those being low voltage digital input, 11 of those being high voltage digital input, and 18 being digital output. 2 different channel configurations were considered as a part of this project. This is a top view of the cabinet. And to better explain and scale, I have a section of channel here with FTA mount. In a typical installation, this 3-foot section will comprise half of a 6-foot continuous section of channel. Each card mounts in the center, and on the left-hand side of the card, the field wiring is mounted, while on the right-hand side of the card, in this more narrow trough, the internal wiring, IOP wiring, is mounted. In this 4-channel configuration that was initially considered, there are 4 channels which greatly increase the capacity of FTAs that can be mounted. However, the cards on the left side and right side must be low voltage. They must contain FTAs, field termination assemblies, less than 24 volts DC. No voltage restrictions are applied in the 3-channel configuration. After partitioning, it was determined that all low voltage or 24 volt DC cards were able to be partitioned into 1 channel. Therefore, the 4-channel configuration was not required. Here we have an example of the actual FTAs that will be used in this project's implementation, mounted in their channels. On the left, we see digital input FTAs. There are 2 mounted in here, 32 points apiece. Each card is 18 inches tall. On the right, we see the digital output FTAs. These cards comprise 16 points, each being 12 inches tall. As mentioned, on the right-hand side of the channel, we have IOP, or internal cabinet wiring. And on the left channel, we have field wiring. As a part of this design project, a power system calculation was performed. Each Honeywell power system can provide 20 amps of continuous 24-volt DC power. Each piece of hardware has a manufacturer providing current draw in milliamps. After completing the system calculation, it was found that the total system will draw 16.41 amps. Thus, a single power system is necessitated. Other reasons for multiple power systems would be to create system redundancy. Also, as a part of this project, an economic analysis was performed. Project labor hours were compiled over the course of the design process. A labor rate of $20 per hour was used for the student team members, while a labor rate of $100 per hour was used for the PCI Skanska and faculty members. A total project labor cost was calculated to be just under $11,000. With 525 project points, the calculated labor cost per point was just under $21. This is a common industry practice. Firms that provide such engineering will have a proprietary number that they will assign as a cost per point. This is useful when initially bidding the project. To conclude, 525 burner management system points were engineered. The hardware selection was finalized along with the hardware layout. The design has been validated by PCI Skanska engineers and designers. The path forward for this project includes NFPA, which is the National Fire Protection Association 85 certification. Code 85 is a boiler systems combustion hazard code that is used for the approval of all fuel burning equipment. Next, controller programming by third parties will take place, followed by the production of a construction drawing package and accompanying scope of work. Finally, implementation and checkout will be completed. Through the checkout process, each point will be individually checked not only for continuity, but for functionality. I'd certainly like to acknowledge several people that not only influenced my project, but really my journey through the USI engineering program. From USI, I'd like to sincerely thank Dr. Paul Cuban, who served as my academic advisor here at USI, Dr. Lara Gracia, who served as my project report advisor, and Donna Moore, whom I'm sure I'm echoing the sentiments of previous presenters, but she certainly seems to have the answers. And next, from PCI Skanska, I'd like to thank Mark Dahlgren, my director, for providing this project, and his group of talented engineers and designers, and Nick Schenk and Dave Lottis for providing their knowledge of control systems hardware and software. Lastly, and certainly most importantly, I'd like to thank my family. They've been a steadfast supporter of my academic career, and most importantly, I'd like to thank my wife, Katie. She has truly inspired me to perform at my best. I'd be happy to take any project questions at this time.
All right, questions?
Back up one slide.
Sure.
What did you have to pay to use this, the new logo?
It was, it's a generous fee, but especially since it's trademarked now.
That's my only question. Anybody else? Any other questions? Why didn't you use the eagle?
That is the USI Sports logo. This is the academic logo.
Good answer. Good answer. All right, let's.
You mentioned 2 other plants within the system. This is a 2-part question. Part 1, what is the likelihood that this design will continue into the other 2 plants? And if so, how would the design vary in the next 2 plants as compared to what's been done today?
It's a good question. The next unit is a mirror of Unit 2. Unit 2 will be the first plant control system upgrade to be implemented. Unit 1 will follow. They are mirror copies. But prior to commencing any of that, a detailed field verification will be completed to verify that the plant-provided prints and database are accurate. The subsequent plant, the third one, is different than the other 2. It will require an even more detailed field verification, and the design will likely be considerably different than Unit 1 and Unit 2 from Summers.
All right. Any other questions? Let's give them a hand.